In this lesson, we're going to introduce resistors in parallel circuits. So when two or more resistors are in a parallel circuit, the same potential difference is applied across each of them. So the potential difference V is applied across each of our resistors. The rate at which the current passes through each resistor is inversely proportional to the resistance of each resistor. So let's just draw a diagram and kind of analyze all these properties. So that was one resistor. Here's another resistor parallel to it. And let's just do another resistor parallel to that one. Okay, so this is resistor number 1, resistor number 2, and resistor number 3. We'd also have current I1, I2, and I3, but 1, 2, and 3 all combined is just I. And then same with our output, it'll just come back out as just I. But as it's going through the 3 different resistors, the current is going to split in 3 ways. But it's the same potential drop, which we call V. So the total current I is equal to I1, I2, I3 coming from the 3 different resistors. We also know that to calculate I, it's the potential difference or potential drop, depending on the type of question we have, over the resistance. So if we're looking for I1, then all we need is V over R1 and so on if we want to find I2 or I3. Now, when we're talking about finding the current through each resistor, and we know that it's inversely proportional to the resistance of each resistor, that means that we can derive the following. 1 over R is equal to 1 over R1 plus 1 over R2 plus 1 over R3. Again, that's because we know that they have a relationship of inverse proportional. So for drawing another case where we have 2 resistors in a parallel circuit, this one is R1 and this is R2, we know the relationship at the rate of which the current passes through is going to be 1 over R is equal to 1 over R1 plus 1 over R2. And if we want to solve for R, in this case, it would be 1 over R1 plus 1 over R2, but inversed. So we're going to go ahead and apply these to specific scenarios. A 5 ohm and a 20 ohm resistor are connected in a parallel circuit, and a potential difference of 100 volts is applied across them. We want to find the equivalent resistance of the circuit, and we want to find the current that flows through each of the resistors. So I'm going to label this as A, finding the equivalent resistance, and then finding the current, which is going to be part B of the question. We're looking for the equivalent resistance, so I am going to use this relationship over here that we just found out. To find the equivalent resistance. So we know that then R is going to be equal to 1 over R1 plus 1 over R2, and then taking the inverse of it. So the first one we have is for R1 is 5. The second resistor is 20 ohms. Need to get a common denominator in order to add. So I'm going to multiply the first fraction by 4 top and bottom. So we're going to get 4 over 20. And then we still have a plus 1 from the second fraction. I just combine it because now it has the same denominator. So that's going to be 5 over 20. And then we're going to inverse that, or reciprocal it. So that's 20 over 5, which is 4. So our resistance, our equivalent resistance is 4 ohms. The next thing we're going to do is find the current that flows through each resistor. So I'm looking for current number 1 and also current number 2. Current number 1 is calculated as the potential difference over the first resistor, and for the second current be the potential difference divided by the second resistor. So this is going to be 100 over 5 ohms, which is 20 amps. And then for the other current, our potential difference is 100, and the resistance is 20 ohms, which gives us 5 amps. So if we're looking for the current altogether, that would be 25, because that'd be 20 amps from the first one, 5 amps from the second one, so it's 25 amps altogether if we're looking for the total current. In this next example, we can combine parallel and series resistors. We can find the solution by solving the parallel sets into a single resistance. So we're going to find the total resistance, the current through each resistor, and the voltage drop through each resistor. So I'm going to draw the diagram on the side that we're going to use. And we're going to say that we have 100 volts. That's your first resistor. Then I'm going to draw a parallel one. And then lastly, another one here. So this is called R1, and it's going to be 10 ohms. This can be R2, and that's going to be 15 ohms. This is R3, and it'll be 10 ohms. And lastly, this will be R4 at 15 ohms. Okay, so we're going to find the total resistance. And for R1 and R2, that's easy. It's given to us as 10 and 15. But the parallel part of it, we're going to have to combine R4 and R3. So the equivalent resistance for that is going to be 1 over R3 plus 1 over R4, then reciprocaled. So R3 is 10, R4 is 15, 1/10 plus 1/15 is about 0.16 repeating. And then reciprocaled, so 1 over 0.16 repeating is about 6 ohms. So then our total resistance is going to be the first resistor, which is 10. The second resistor is 15, and then the combination between R4 and R3, which was 6, we just found, and the total resistance is going to be 31 ohms. The next thing we're going to do is find the current through each resistance. The only thing we can really find right now is R1 and R2. We probably need to do a bit of part 3, which is the voltage drop through each resistor, because we need to find V in order to find the current through R3 and R4. So I'm going to do part of B for now. So we know that V is equal to the current times resistance. In this case, I'm looking for the current. So it'll be V over R. Now for V, it was given to us in the diagram, that's 100 volts as our potential difference. And the total resistance we just found in A, it's 31. So this is 3.5 amps. This will be the current that goes through R1 and R2 in the series. Now, if we look through the current through R3, to calculate that, that's going to be I equals V over R3. But the thing is, we don't know what the potential difference is here. You're going to have to find that V first. It's not the same as 100 volts because it is in a parallel set. So I'm going to move on to part C for now and look at voltage drops. And that will help me determine what I'm going to put in this V here, because that whatever I calculate for the potential drop is going to go in here. Okay, so for the voltage drop, we're going to analyze it as R1, R2, and then our equivalent, because the equivalent is going to include both 3 and 4. So for R1, it's going to be V is equal to I times R. The current we found already in part B is 3.5 amps, and the resistance for 1 is 10 ohms. So that's 35 volts for the voltage drop. For R2, similar calculation, our current is 3.5, which we found in part B. Our resistance here is 15 ohms. So then our voltage drop is going to be 53 volts. Now for the equivalent resistance, we're going to use the current again. This is the current for the entire thing for our parallel set, but it's not for each part. So we can't just divide 3.5 by 2 and say that that's our voltage for R4 and R3, but we just know the combination of R3 and R4 will be 3.5. So I'm just saying I for both. Because it's in a parallel set. And then we already calculated the equivalent resistance in part A for R3 and R4, and that was 6 ohms. So altogether, this is 21 volts. And that's what we needed to find the current through each. So we're going to use this 21 volts and insert this into here. So then now I can finally find the current that goes to R3 because I have the voltage drop. That's 21 volts, and then R3 is 10. So that's going to be 2.1 amps. And I can also find R4. Again, V is 21. Because of the potential drop we found in part C, and then R4 is 15. So then the current that goes through R4 is going to be 1.4 amps. And just take a note that if we were to add 2.1 amps and 1.4 amps, we're going to get a total of 3.5 amps, which is exactly what we needed. So exactly what we needed to satisfy our current, which is 3.5 going through R1, R2, and our equivalent, which is both R3 and R4.